So there again, uh, continuing where I left off. This is where we left off last time with the what I described as a clever demonstration of the associative property as applied to these permutation groups. Well, still, as of yet, not known to be a group, but a set, and the set of permutations on n objects, together with the composition product. That set is closed and it obeys the associative principle. And now we could go on to the rest, which I have here. And I had a few things I wanted to say first off before going on. One, please disregard the screaming child outside. Whatever its reason for screaming is, it's nothing to do with me, so I'm not going to get involved. So now what we've shown so far is that the axioms wanted to hold closure and associative. And what I started writing down here was for the potential group of permutations of n unique objects, and that part I made fairly explicit at the beginning, that the objects are all different, like numbers 1 to n. But I wanted to point out that any properties that hold for these groups of unique permutations of unique objects will also hold for groups containing either duplicate or duplicated elements. And the reason that's true is easy to prove to yourself anyway, is that the reason that's true is that we can always regard, if we had a group, permutations, or any kind of group of elements that had a similar property to one we know is a group containing only unique elements, the properties should carry on through to those groups that have duplicate elements. And the reason, again, is easy to explain to you, either from me to you or you to yourself, because we can regard the so-called duplicate elements as unique in themselves, if we like, but in a special way called, I would use the word degeneratively. Okay, so that is the duplicate elements are different elements, but they have some property in common. In this particular case, the property they have in common is that they're equal to each other. Now, that might sound like crazy talk, but there are precedents for that. For instance, a deck of playing cards may and is often considered as a collection of 4 identical sets of 13 cards, right? Put together, from ace to king, but it could also be regarded as a collection of 52 unique cards if we want. And since this collection of objects is the same no matter how we look at it, the two sets generated, in this case permutations, any group built from one or the other of these two identical sets using an identical operation ought to behave identically in the latter sense. So whatever we know that is true about a collection of unique objects will also apply to a collection where we have repeats, and we just regard the repeats as different. Then when it comes time to say something else, perhaps about the group, we can use their common property to make further deductions. Okay, so it's not totally restrictive. You could imagine a collection of things where some of the elements are in fact the same. Okay, so now moving along with our set of n objects, or permutations of n objects, not the objects, but the permutations. We want to prove the existence of an identity element, in particular a right identity, and a right inverse for every element in the set. Okay? Because those are the axioms that we're using, you could equally use left axioms. So you could use the left inverse and left identity axioms because they follow from one another. Or you could use the set of axioms that includes neither left nor right, but both. In either case, you have to be consistent. If you're going to use the right inverse in your set of axioms, then you have to choose a right identity in your axioms. Then you have to show the existence of a right inverse. It's no good to show the existence of a right identity and left inverses because those are not of the same category, and it doesn't follow that the construct is a group if we have right identities and left inverses. We don't know anything about that. We haven't looked at that case, and so at this point we wouldn't be able to say anything about that. Okay. Well, as far as identity goes, the obvious choice for identity, the permutation, which does not do any permuting, is a right inverse, a right identity for our potential group. Okay, and here I've proven that. It's not very hard proof. So all this does is, given I, the output, if you like, is I. So 1 goes to 1, 2 goes to 2, and so on. Taking that and the composition of that with another permutation, that permutation on the left and this thing on the right, gives us, by the rule of composition, I goes to I sub k sub I. Okay? We'll just replace I with, we take I right here and replace whatever its index was. This can be written like this, I sub I, if you like, which just means I. That gives us this, right? You could go directly from this line to this line as well, if you like, right? We take this thing says replace I with whatever is in here, and whatever is in here happens to be I. So, doing the composition, replace this with the value obtained from this permutation for I, which is k sub I. So you can write it this way. So in fact, the way I've written this is really more equivalent to that. it means the same thing. The ith I, which is I, the 10th index from 1 to 10, is 10. The second is 2, and so on. Okay, so it's a right identity. You can also just use numbers to verify by example very quickly that's all this does, right? It turns out that it's also a left identity, although we don't need to know that. But we can multiply it out and see, and it turns out that it is. If I do this, if I multiply these two, compose these two, the rule again is I take this thing and replace it with the output of this thing, which gives me k sub I sub I, which is what we started with, k sub I. And I mentioned that here. We didn't have to prove the second property, because that will follow if we can prove the existence of a right inverse for every element of the set. Because then we would have a group, and everything that we know about groups will suddenly follow. Alright, now a right inverse of a permutation, in fact, is simply the one that takes not the elements, but the indices, really. This element doesn't refer to group element, so this should maybe be written indices back to themselves. So I goes back to I, 2 goes back to 2, and so on, from where they began. So if we start out with a permutation like this, the result of multiplying by a multiplying by an inverse permutation, we want that product to bring I back to what we started with. And the permutation that does that is this one. This is a right inverse of I sub I and I, which takes I to k sub I. That's easy enough to prove. Okay. Well, I just said that. I didn't prove it, did I? I just said it. Well, it is true, right? It does follow immediately that this is true, by definition, right? Because what this thing does is it takes the result k sub I and turns it back into I, right? So the composition of this on the right with this thing has the result of taking I back to I. I should have made it more explicit. Okay, so that fact, I could write it in the corner here quickly, that you can see immediately. That if I had this, and compose that with this thing, and by definition of composition, right, we take the definition of composition is first we apply the first rule, and that gives us k sub I. Then we apply the second rule on the first rule. So this takes k sub I back to I, right? So it follows very quickly and trivially. But this whole thing together results in the I to I permutation, no permutation whatsoever. That being the case, it immediately follows that K sub I is also a left inverse of the same permutation, just by virtue of its existence, because by demonstrating the existence of a right inverse, we've shown that the thing is a group, and that the set of permutations of n objects under the composition product is a group, and that satisfies all of the right-handed group axioms. So it immediately follows that any right inverse is also a left inverse, and any right identity is also a left identity, and is the only identity which is unique. So it also follows that the identity and inverse elements are unique as applicable, meaning a given inverse is unique for a given object, but it's not the only inverse element in the group. It's just as the word unique is meant to apply for the particular cases. Identity is unique for the entire group. It's raining now, and I know I'm raising my voice, and I probably don't have to. Anyway, I'll try to not shout. So here's an identity for the group we're looking at, now known to be a group of permutations of 4 objects, 4 items. Its inverse being given this way. Okay, the inverse is basically you turn it upside down. And I've given an example here. This one I just pulled out of a hat. To construct the inverse element, you just turn it upside down, like this. Now I can rearrange that into this form by moving the columns. I'm allowed to. Moving the columns has no effect on how this permutation behaves. So it's best to have them written in order. This is the permutation written in the standard format for this object. Okay, we can multiply them out, and you will observe that it is in fact the inverse. 1 goes to 3, 3 goes to 1, 2 goes to 2, 2 goes to 2, 3 goes to 4, which goes back to 3. 4 goes to 1, which brings you back to 4. Okay? And yeah, I just made a note. Also demonstrates the interchangeability of the columns when we write them out this way. Okay, moving along. Now I just wanted to give another example of a permutation group, a smaller one, but slightly smaller than the last and bigger than the second, bigger than 2. The group of permutations on 3 elements has 6 elements, and I've written them out, all of them here. Okay. Now there are no others, and it's easy enough to verify that. Maybe I should pause, but I can't hear myself. Well, it's not letting up, but I just thought anyway. I'll turn it off again, but I don't think I emphasized clearly that at this point, from this point onwards, we're talking about a group. I'm going to put these in a different color to indicate that something happened, but anyway. And that something from this point onwards, we're talking about a group, the group of permutation. Because of the existence of that right inverse element satisfied the last of the four axioms. I don't know if it was stated here. It wasn't stated. I said it will follow if we find a right inverse for each element. Then we will have completed the proof that all axioms are satisfied, in which case we're talking about a group and not a set anymore, and we can begin talking about things like inverse and identity and so on, which we have. Well, it's dying down a bit now with rain. Okay, like I said, just sticking with the permutation groups for a minute, I thought that I'd take one that's take the one before the fours as being of a manageable size, and just quickly have a look at and see if there are any properties and things that we might be able to find out about it. And in the meantime, define something called a subgroup. Okay. Now, if a set of here's the collection of 6 elements that comprise the group of permutations of 3 anythings. Okay. Group of permutations of 3 elements. I actually gave a label to this type of group, P sub 3 if you want. Okay. Permutations, and it has 6 elements, not 3. These things are not elements, these are just indices. As far as the elements go, if you can find a collection of elements within, but not equaling, so a subset essentially, in a group, that is itself a group, that is, it satisfies all of the axioms. Now that's not true of any collection of elements within a group, right? In particular, the closure principle has to be satisfied. And a subgroup is, if it's a group, it's closed. So if it's smaller than the group, it's a thing all by itself of smaller size that internally behaves in every respect as a group. If such sub-collections can be found, they would be called subgroups. That's the definition of a subgroup. It's a subset of the elements of a group that is a proper subset, smaller than the group, and satisfies the 4 axioms. And as an example, every single group contains at least one subgroup, and that is the identity element by itself forms a group, turns out. It has an identity element, that much to be sure of. Each of its elements has an inverse, namely itself. It's closed, I times I equals I, and it's associative. I is in fact associative. It's also commutative and a bunch of other things. So there is at least that one. If we look at this collection, are there any subgroups we can find in here? Just given the looking at them, not trying to figure out how I generated this list. Because if you knew how I generated this list, then it would be very, very much easier to identify the subgroups that are there. And in fact, there are 4 subgroups that aren't trivial ones. You can consider this the group itself, if you like, as a subgroup. It's not really a subgroup, it's the group. But I is the trivial case, but there are 4 others that contain more than one element, turns out. And there are no others. There are no other sets that are subgroups, and I hope I'm not making a mistake in that, because there are many theorems to do with subgroups and how many one should find, and their relation to how many there are with the order of the group is of a particular nature. And I say that there are 4 that I found, and one other, these 3 and one other, plus that makes 5. And I can't remember what the theorem is, but I believe that the number of subgroups maybe not the number of, I'm not sure. But see now 6 here, the number 6 itself can be thought of as 2 times 3. And then it's fine. The theorem I'm thinking of says that the order of the subgroup, any subgroups found, is always a divisor of the order of the group. So these all have 2 elements, and 2 divides 6, so we're okay. And the other one is of size 3, and 3 also divides 6, so we're okay with that one too. These ones, each one, this is I here on the left all the time. These contain 2 elements, and the other element of these ones, of this collection, is its own inverse. You multiply this by itself, compose or whatever, you get I, you get this. See, 1 goes to, if you can do it in your head, I don't know. 1 goes to 2, and then 2 goes to 1, so I would get 1. 2 goes to 1, and 1 goes to 2, and 3 stays the same. Similarly with these. Now, if I had done something else first, like show you the permutation group on two elements, right? That is, you just have 1 and 2. Let me give you a sample. How many elements are there in this group? Well, there are only 2. There's this one and this one. Right? This is P2 if you like. If this is P3, this is P2. Here's its identity, and here's its other member. This thing times itself gives I back. I know it's a group because we already proved this thing's a group, and every element has an inverse, and it has an identity, and they're all unique. So if this element is to have an inverse, I know it can't be the identity because this times identity doesn't give identity. It gives this, right? The flipping. So it must be its own inverse. In fact, it is. If you multiply this by itself, if I did this, multiply these two, 1 goes to 2, which brings me back to 1. 2 goes to 1, which brings me back to 2. See? Now all these 3 subgroups are generated by taking any 2 of the 3 elements and flipping them in the permutation or whatever. Okay? So that means each of these has a trivial 1 number that that brings itself to itself, in this case 3, unions with this group, some form of this group. This one has 2, right? Unions with this group where it's using 3 instead of 2. So this has to be its own inverse. Similarly, this one has 1 that takes itself to itself, unions with another version of this that uses 3 and 2. So these are all their own inverses, and there are only 3 possible ways to do that, with 1, 2, and 3. So I can generate 3 subgroups like that. Another subgroup, save this, save, that you can find in this group is this one. I've actually given this one I've given it a name, haven't I? I've called it R of P3. This is the rotation, a rotation subgroup, where what this does is it rotates the elements underneath. So here's the identity. I'm going to take that identity, and if I slide the numbers to the left and take the one that falls off and put that on the end, I get this. If I repeat that same trick, I get this. Well, it turns out that this here is a group all on its own, and it has 3 elements. Okay? If you try it, one way to be sure that it's a group is to just multiply these 2 and notice that you get this one back. That would have to be the case, in fact, because for a similar argument from before, if that didn't happen, then then it would have to produce a different element, and therefore there would be more elements than 3. Also, these can't be their own inverses because I've already covered all those cases, and they're not. This times itself doesn't give itself back. Okay, so let's see, R1 times R2. R1 times R2 is already placed nicely. 1 goes to 2, 2 goes to 1, so 1 becomes 1. 2 goes to 3, and 3 goes to 2. So 2 became 2, and I don't even have to check the last one. 3 must go to 3, because we know that we're going to get a permutation back, and so far we got 1, 2. The last one has 2, and I don't even have to check it, it has to be a 3. Now, notice that since that's true, that the inverse of this here, I've labeled R1, the right inverse, rather, is R2, right? Its right inverse is R2. Now, I can't take it for granted, I don't think, at least not without proof, that right and left inverses are the same in a subgroup, right? In fact, I know I can't take it for granted. Yeah? Maybe I can. But I haven't shown that, oh no. I can't take anything for granted. If I want to show this as a group, I have to do this before. We do have already, by theorem, that the inverse of just the fact that this is a group, it's closed and it obeys the associative property and all that, follows from the fact that it's a subgroup of a group. So yes, you can take those things for granted. And it's been proved for the elements of the larger group. Those properties are true of any subgroup. So the inverse of R2 therefore is R1, because R1 is a left inverse of R2, and so therefore it must also be a right inverse, because there's a 1 and only one inverse of R2. That much we've already established, it turns out. In fact, to find a subgroup, all you need to do is find a collection including the identity that's closed, because all of the other properties follow from the fact that these elements are taken from a group. So they're associative. If the identity is a left-handed identity for one element, it's also a right identity. If one element's an inverse of the other, inverse for another, then it's a left inverse, right? Right and left inverses are the same, and so on. Okay, so now it turns out that R1 times R2 does give the identity, and by theorem we have that this product also gives the identity because of the equality of left and right inverses, right? And we also have this fact that I say by theorem because those things were proven as properties of, these things were proven as properties of groups, and this is a group. So, every element in this group, including I times I, is equal to I times the same element in the other direction. For the R1 and R2, you get R1 or R2 back again. What I'm trying to show here in a roundabout way is that for this particular subgroup, the products are commutative. That is, it works backwards and left or right. A times B equals B times A for all of these elements, it turns out. So as said here, composition of any two elements of this subgroup happens to be commutative. So the group, in this case, is said to be commutative, or the more common term abelian is used. I was just going to, or I did, continue on explaining who this mathematician Abel is and was, and important if that is. Before doing so, I want to do this. That has not been shown, and in fact it's not even true. In totality, this group P3 is not an abelian group, and that can just be shown by example. This subgroup is, but the group in total is not, and the counterexample is easy to find. These two do not commute, it turns out. So let's see if I can. I wish I had a big eraser. Get rid of, just make some space here. I thought that if all of the subgroups were abelian, and they are, that implied that the group itself is abelian, but it doesn't. And here's a perfect example. I want to draw a circle around that and delete it. As you can see, these are all abelian. A times B is certainly equal to B times A for all of these, and the other subgroup. But these two, which are not, one of which is the last one of this subgroup, and the other is the first or the second element of the last subgroup. These do not commute, turns out. If I call this A and B, AB equals 1 goes to 1, and this one takes 1 to 2. Okay, 1 to 1 to 2. 2 goes to 3, which takes back to 1. And the last one will be 3. 3 takes us to 2, and 2 goes to 3. On the other hand, BA does not give the same result. 1 goes to 2, which 2a takes to 3. 2 goes to 3, which a takes to 2. And 3 goes to 1, which a takes to 1. And they're not the same, and therefore a, b, and b are not the same. So even though all of the subgroups of this group are abelian, the group itself is not. Now, this might be part of a more general theorem on products of elements that are from different subgroups, but I'm not sure about that. I would have liked to spend more time talking about Abel, the mathematician, who in fact invented group theory. Well, him and another one called Galois are both around the same time period, invented group theory independently. Abel, who only lived a very short life, died at age 26, was nevertheless an extremely important mathematician and contributor to the study of mathematics, writing this page. One thing you might be thinking, and that was probably, this is probably what led me to realizing that I'd covered everything. One thing that you might be thinking is that I've left something out, and I thought so too. And I was thinking in terms of Euclid and those triangles, and how I was saying you have the triangle, and then there's a similar triangle that's a mirror image of the first triangle, and you can't obtain by rotation, right, from that triangle, the mirror image triangle, right? That's a different sequence, a different permutation of the sides, which can't be obtained through rotation. So here's a thing, the last one, the last subgroup, rotation group. Here, well, isn't there one missing that corresponds with the other collection of rotations? And the answer is no. Why? Because you can form that collection. See, first thing you have to scratch out of that collection is the identity, because the identity is not a rotation of the other set of permutations. And that leaves you with this collection, and this collection is not a group because it doesn't have an identity element. See what I'm saying? So in the world of group theory, although you can certainly talk about that, you can talk about this collection of symbols, they don't form a group. So they haven't been left out, they just don't form a group. It's also true that if you take any of those other ones that I showed you, these ones, and try to add another element, either from here or from the other set, with it, you will not, that will not form a group. Although it's true this one has an inverse, and this would have an inverse, say if I plopped it in here, the product of these two is not an element of this set of three. If you see what I'm saying, if I took these three together, the product of these two is not within this set. In fact, it gives another one, and that other one is not this one. Sorry, where is it? This one? Yeah, it's not this one. It's in the other. It's one of these two, I guess. So these are the flips. Yeah, 1, 3, yeah. These are the flips, and these are the rotations, and that's how I generated these numbers. The product of any two of these flip things gives you a rotation thing. So you end up with, in order to satisfy the closure principle, you end up generating all 6 elements. So this is in fact the totality of all possible subgroups, and whether or not the group is abelian or not, I think follows from this breakdown. Either an element is in one of these subgroups, right? In which case its inverse is itself, okay? Or it's going to be in the other subgroup, which contains all of the remaining elements of P3, right? And the product of these things, which is an abelian product. I know it's true. I haven't shown whether or not, and you can try it at home. This times this is equal to this times this. Maybe it's not. If it isn't, then it's not abelian. But in fact, I'm pretty sure it is abelian because the first non-abelian finite group, I think, is order like 48 or something. No, is that true? No, that's not true. But I think it's more than 6. 9 maybe. I saw it written somewhere. I was curious where. Somewhere in here. I can find it again. Somewhere he gives the order of the smallest possible non-abelian subgroup group, and everything before that has to be abelian. Another thing I haven't mentioned is this degree idea. We have the group's order, which is the number of elements. Okay, I'll get to that other thing. There's one more thing to say about permutation groups, very important, which I'll get to next time. And that is this section 6 of the book that I'm reading. That shows you how you can write down groups in terms of something called a cycle. Okay, there's a natural cyclic tendency to do with anything finite. Everything in one way or another forms a kind of cycle. And in fact, groups can be written as products of cycles, believe it or not. The cycles are written in this funny form. Okay. Now, forgetting about how this was derived, you can see that whatever this means, this is a type of product. And this product apparently represents this permutation. Okay? However that works. Now, okay, here is the group of permutations of three things that we've been looking at. Alright, and it can be represented in terms of products of cycles. It's not the same as subgroups. These are not necessarily, this for instance is probably not a subgroup. And 4 is this. And anyway, this method of being able to write things down as cycles tells you that every permutation can be written as the product of some form of cycle. Okay? And the cycles themselves are permutations. Or they correspond to permutations. And it's easy as well to show that that decomposition is unique. So there's an interesting analogy between these cycles and numbers. That is, here's a permutation. This is its factorization. This is it factored into primes, if you like. Okay? So there's an interesting analogy between numbers and how you can break down a number into a product of primes, and permutations, which you can break down into a product of a more primitive thing that cannot be broken down any further. Okay, well, till then, see you.